All right, so welcome to Chapter 8, Introduction to Inferential Statistics. The z-test, what it is and what it does. Confidence intervals based on the z-distribution. The t-test, what it is and what it does. Confidence intervals based on the t-distribution. So the chi-square, goodness of fit test, what it is and what it does. And then finally, correlation, coefficients, and statistical significance. What the z-test is and what it does. So the z-test is a parametric inferential statistic test that of the null hypothesis for a single sample where the population variance is known. Okay, so it's going to rely on sampling distribution. That's one of the requirements. A distribution of sample means based on random samples of a fixed size from a population, and that's the key point there, fixed size. And the standard error of the mean, the standard deviation of the sampling distribution. Okay, this will make a little bit more sense, hopefully, as we go along. Central limit theorem states that for any population with a mean mu and a standard deviation sigma, the distribution of sample means for sample size n will have a mean of mu, will have a standard deviation of sigma over the square root of n, the number of the sample size, and will approach a normal distribution as n approaches infinity. So the larger the n, the more of a normal distribution will occur. The formula for z is x bar, which is the mean of x, minus mu over the standard deviation of the sampling distribution. So sigma x bar. Okay. And usually anything that you're going to work on in this class, you're going to be given most of this information. So it's not stuff that you're going to have to usually figure out. However, if you do need to figure, for instance, sigma x bar, here's the formula. You've got sigma, which is the standard deviation, divided by the population, the square root of the population. So for instance, in this example, we have a mean score, right, for 75 children, which is 103.5. And these are children who are enrolled in after-school programs. So what we know about IQ score is that it's based off of a mean of 100 and a standard deviation of 15. So the standard deviation is 15. That's where we get this number. And we have a population sample, or a sample of the population of 75 kids. So you're just going to take the square root of 75, our sample population, and then you got 15 divided by 8.66, which equals 1.73. We are now going to use sigma x bar and plug it into the z. Now remember, z is just a standardized score from raw population scores. It just puts it on a normal distribution curve, and that's why it's important, because we're going to figure out what is the probability here in a minute about getting these 75 children. Is 103.5 greater than kids who weren't enrolled in after school programs? That's going to be kind of the test that we're going to do. So we are going to do a one-tailed z-test. The value of the test statistic that marks the edge of the region of rejection in a sampling distribution. Values equal to it or beyond it fall in the region of rejection. The region of rejection, the area of sampling distribution that lies beyond the test statistic's critical value. When a score falls within this region, that is, our null hypothesis is rejected. Okay, remember HO is null hypothesis. So when we look at the test score here, if this is a normal distribution, for Z, we are looking at 1.645 being where we're going to reject it. And our value from the test was 2.02. So it is in this region of rejection. So we would reject the null hypothesis and accept the alternative hypothesis, which is that the students who attend after school programs have higher IQs. that would be true, or at least within this test statistic, it is shown to be true. Okay. So suppose that in the previous example, we do a two-tailed test. All of the measurements are the same. But now, when we look at the test statistic, we are looking at the alpha, which is the amount of error that we're allowing for to be 0.05. And over here you have 0.05. But because it's doing a two-tailed, we're going to double the alpha. So now it becomes 0.025 is the critical value. And so that is going to make it from 1.645 to plus 1.96. And now what we have is it still falls within it, right? Because it was 2.02. So we're still good to go as far as rejecting the null. Which means in this case, because we did it a two-tailed, that it's not going to be equal. We just didn't give it direction. So now that we know that it's not going to be equal, and it wasn't going to be equal in the first test that we did. And we'll do some examples when we're together. I'm going to record for this afternoon the actual in-class stuff. If I'll edit it so that if I'm just sitting here by myself not doing anything, then no reason to record that. So, but if we are doing something, and I plan on working some of the problems out of the textbook with you so that you can see how these things are done. A one-tailed test, statistically a more powerful test than a two-tailed test. And that's because anytime that we can find directionality, that's more powerful. Statistical power, the probability of correctly rejecting a false HO, a false null hypothesis. With the one-tailed test, we are more likely to reject the false or the null hypothesis. The z-score for OBT does not have to be as large to be considered significantly different from the population mean. Yeah, so as the sample size increases, the standard error of the mean decreases. The test is appropriate to use if the parameters such as mu and sigma are known. And we must use it with interval and ratio data. The t-test is appropriate to use in cases where the sample size is small or where the sigma is not known. So, and remember the sigma is standard deviation. So when we look at confidence intervals, it's an interval of certain width that we feel confident will contain the mean. The formula for the confidence interval is x plus or minus z of the standard sampling deviation. Okay, so the standard error of the mean. And the z-score represents the desired confidence interval. So statisticians recommend 95% or 99% confidence interval rates, right? And like I said, we're going to do some of these during the online portion of class today. So don't worry too much about it. We'll go over these. The t-test, what it is and what it does. Again, the t-test is another parametric inferential statistic test of the null hypothesis for a single sample where the population variance is not known, okay? So again, we don't know what the sigma is. We don't know what the standard deviation is. So that's why we use the t-test. The student's t-distribution, a set of distributions that, although symmetrical and bell-shaped, are not normally distributed. So now we have an introduction of degrees of freedom, and that is the number of scores in a sample that are free to vary. In general, the degrees of freedom are usually equal to the sample being tested minus 1. And so Again, it's going to depend on what we are doing, but looking at an alternative hypothesis. Okay, so this one, again, the null hypothesis is that the mu is going to be less than or equal to the second mu 1. Or biology students are going to be less than or equal to general population. And I don't know what the actual question is, but we're looking at whatever we're assessing in biology students is going to be less than the general population. And so the alternative hypothesis is that biology students is actually going to be greater than the general population. So that's what we want to show, is that whatever we're testing for, we want to reject the null hypothesis and accept the alternative. So this is saying that there is no difference or less of a difference. This is saying that there is a difference in that it's greater in biology students. So the t-test is x bar minus mu over the sample deviation. Okay. Standard error of the mean, I mean. Estimated standard error of the mean and estimate of the standard deviation of the sampling distribution. So it is the sampling standard deviation. So I was correct. I just said it in a different way. Formula for the sampling standard deviation or the sampling distribution is S over the square root of n. So it's exactly like the sigma, but now we're using the S instead of sigma, and the number of individuals participating would be the same. So in this case, in APA style, the result is reported as T, the degrees of freedom, which is 9 in this case, so we're 10 participants, equals 2.06, where the P is less than 5%. Okay. So in the two-tailed test, we're just looking at they are different in either way, and we get the same test score. What is the difference between the two-tailed t-tests? The critical values differ. So remember, it's harder for this directional one than it is for the non-directional one. With the two-tailed alternative, the region is divided evenly between the two tails of the sampling distribution. With exactly the same data, we rejected with a one-tailed test, but failed to reject with a two-tailed test. So one-tailed tests are more powerful than two-tailed tests. The assumptions of the test: data are interval. In order to use the t-test, data must be interval or ratio. Population distribution of scores is symmetrical, and that's an assumption. The t-test is used in situations in which population mean is known, but the population standard deviation is not known. So sigma is not known, but we use S for the sample standard deviation. If these criteria are not met, a non-parametric test is more appropriate. And again, this is the confidence interval for a one sample t-test. The confidence interval is determined by x bar plus or minus the t-test times the standard deviation of the sample. And again, 95 to 99% confidence interval. Chi-square, goodness of fit test, what it is and what it does. The chi-square goodness of fit test is a non-parametric inferential procedure that determines how well an observed frequency distribution fits in an expected distribution. Observed frequency, the frequency with which participants fall into a category; the expected frequency, the frequency expected in a category if the sample data represent the population. So for the formula for chi-square is chi-square equals sigma, so that is uppercase, and this is the total of observed minus the expected squared over the expected. So O is the observed frequency, E is the expected frequency. In APA style, we have chi-squared, 1, the degrees of freedom, n equals 80, and this is equal to 4.24 for whatever test that they did, and the alpha was less than 0.05. And so assumptions and appropriate use, appropriate for nominal, so categorical data. The frequencies in each expected frequency cell should not be too small. So again, you need to have some population, and each cell has to have a fairly decent amount of people or participants or whatever it is that you're measuring. The sample should be randomly selected and observations must be independent. And again, those are the assumptions. And finally, the correlation coefficients and statistical significance. A one-tailed test of correlation coefficient means that we have predicted the expected direction of the correlation coefficient. A two-tailed test means that we have not predicted the direction of the correlation coefficient. Degrees of freedom for the Pearson product, n minus 2, where n represents the total number of pairs of observations. So, and again, we'll talk about this during the class, online stuff. So I've got my whiteboard behind me. We should be able to get set up and do some good stuff this afternoon. I hope to see you all in the class, and see you in a bit.